So for today's lesson, we're going to start to talk about angle identities. So last year in grade 11, you were given identities that you were asked to prove. So you had your left side equaling your right side. And with your identities, you were given two identities that you could use to rearrange with. You had tan x equals sine x over cos x. That was called your quotient identity. And then you were also given the identity sine squared x plus cos squared x is equal to 1. And that was your Pythagorean identity. And so with those identities, you could rearrange them. You could then use those to help prove other identities. We're going to move away a bit from that today, because what you'll notice in those identities that you learned last year, you had tan of x equaled sine of x over cos of x. The angles all stayed the same. The angle never changed. So you had sine squared x plus cos squared x equals 1. Those angles never changed. If you look at our title for today, our title is angle identities. So how we are moving away from those two identities you learned last year is today we are going to prove how we can actually affect the angle. Okay, so we can change our angles. And so you'll notice the first identity that we're going to start with is a negative angle identity. So I am telling you that this is true, and we will now go to prove it and use it to come up with other identities. So what you'll notice is we can say sine of a negative angle is equal to negative sine x. And I'm hoping just by looking at that, we can see that we have in fact affected the angle. That angle was a negative, but we can say that it is equal to negative sine x, in which we notice in that statement on the right, it has a positive angle. So we are going to be changing our angles. So we're going to have an effect on our angles today. Okay, so let's go through. So this first lesson, we're going to spend some time coming up with some proofs to show this. Okay, so let's first start. We see sine ratio, so that means I'm dealing with a right triangle. So I realize I've given you an axis with a unit circle. I'm just going to jump to the left here to just work on the side as well. So here, if I have a triangle, I think sine ratio, I think right triangle. Okay, so that's what we're thinking of when we're working with this today. So I can also then, to put that triangle onto my axes, I'm going to take my initial arm and I'm going to rotate it, and I can draw a terminal arm in quadrant 1. So there's my terminal arm in quadrant 1. I've rotated this angle x. Whether that's in degrees or radians at this point, we don't really care. Okay, we're going to be working with our angles in radians, but what we just have is an angle x. Okay, so now I'm going to label, let's label the origin. I'm just going to label it D just so we don't get confused. And I can label this as point A. That point that's formed here is point A. And then I'm going to drop our height. And we can label that as point B. So you'll notice we've drawn that triangle onto our unit circle. So I'm just going to jump back, though, to the triangle that I've drawn on the left, just to be able to draw this out. So we know that we have, if this is A, my origin was D, and this is B. So maybe I have triangle ADB. Now let's label those sides. I know across from angle B is side length B, across from D is side length D, and across from A is side length A. For side length B, if we're thinking of our unit circle, we know for our unit circle, side length B is going to have a length of 1. So what does that mean? If I work from angle X here, that tells me that cos of x, so cos from angle x is adjacent over hypotenuse, so that's going to be cos of x equals a over 1, and sine of x is opposite over hypotenuse, so that's going to be d over 1. So what we've just discovered is our side length A is equal to cos x. Our side length D is equal to sine x. So side A could be represented with cos of x. So if we think about that, if I go back to my unit circle, how do I get to A from D? So if I'm going, this is my side length A, how do I get from, I go across cos x, and I go up sine x. So that point that I have, point A, is cos x sine x. So I'm just going to clean this up for a second. All right, so now that gives us part of it. So we are working from our positive angle here. I know that point A can be represented by cos x sine x. So again, those lengths, if I were to label them on, this was cos x, and this is sine x. So now, in order to get a negative angle, I can rotate from my initial arm. I could have rotated and dropped through the fourth quadrant and rotated a negative angle. And so I'm just going to, we're fudging this diagram a little bit because I'm drawing to the best of my ability that those angles are relatively the same. However, we know that because it's an x and a negative x, they should be the same size angle. One's positive and one is negative. So to get to, let's label that as, I don't know, let's label that as point C here on our triangle. So to get to point C, I'm hoping we notice that we still have to go across cos x, and we have to go down sine x, because if those triangles are congruent and they're the same size, then I know I have to go down sine x, which would give me a negative sine x. So again, I'm just going to clean this up for a second. So now, what does this mean? So if we look at our diagram, if I look at my angle negative x, I can say that since sine of negative x is equal to the opposite side over the hypotenuse, and when we look at our triangle, from negative sine x, the opposite side over my hypotenuse, and we know our hypotenuse has a side length of 1 on our unit circle, that's going to give me negative sine x over 1, which equals negative sine x. So what you'll notice is we have just proven this negative angle identity. We are able to affect the angle. The proof for that we can see here on our unit circle. But so now let's use that information to examine and prove our other two trig ratios. So now if I look at this, and if I have cos of negative x, I know cos is adjacent over hypotenuse, So adjacent over the hypotenuse. So cos of negative x is equal to cos x. I know tan of negative x is the opposite side over the adjacent side. Our opposite side is negative sine x. Our adjacent side is cos x. And that's just your quotient ratio from last year. Sine x over cos x gives us tan x, and we have a negative tan x. So we therefore know that tan of negative x is equal to a negative tan x. So those are 3 new identities that you've learned. So those we call our negative angle identities. They are 3 identities that you do need to know. And we should be aware of how we were able to create those identities. So those are our first 3 new identities that we are talking about today, and we will continue to use them over the next couple of lessons. So our next set of angle identities, so again we can change what the angle looks like, is our complementary angle identities. And you guys will remember from grade 9, complementary angles means it adds to 90 degrees, which we'll just turn that terminology to it adds to pi by 2. And so we have our right triangle, and let's just label the triangle. Let's just label it ABC, which then we can label our side lengths. And if I label this angle X, so I'm going to start by just identifying my various trig ratios. So from angle X, so sine of X is opposite over hypotenuse. So sine of X equals A over C, right? From this angle, opposite over hypotenuse. Cos of X is equal to adjacent over hypotenuse, so B over C. And tan of X is opposite over adjacent, so A over B. So there we have our primary trig ratios from our angle X. Since we know our triangle adds to 180, and we already have a 90-degree angle or a pi by 2 angle, we can say that this angle here will be pi by 2 minus x, because we know that the value of those 2 angles, those other 2 angles, have to add to 90 degrees in order for this triangle to add up to 180 degrees. So if we work from our pi by 2 minus x angle, so now this is the perspective we're looking from. So sine of pi by 2 minus x is opposite over our hypotenuse. Cos of pi by 2 minus x is adjacent over hypotenuse. And tan of pi by 2 minus x is opposite over adjacent. And so now when we look at those ratios, what I'm hoping we notice is we notice that we have equivalent ratios here. And what we then can say from that is we know that cos of pi by 2 minus x is equal to sine x. We notice that we also have these are equivalent ratios. So we know that sine of pi by 2 minus x is equal to cos x. And so let's start with those ones, and then we will talk about our tangent. So I have sine of pi by 2 minus x is equal to cos x. Cos of pi by 2 minus x is equal to sine x. And then if I follow along with that, I have tan of pi by 2 minus x. Well, what I notice when I look at tan is they are the reciprocals of each other. So I can say that tan of pi by 2 minus x is equal to cotangent x, which we know is its reciprocal. So those are 3 more identities that we have. Okay, so again, we should be familiar with these 3. We will be using these 3 identities. And we should, though, be able to, if needed, to come up with those identities pretty quickly by thinking about our right triangle, right? So very quickly, it's very easy to come up with what these identities are if we just even think about the angles in our triangle. So one thing that we have to be very careful of is sometimes we're often tempted to expand this. We cannot. You'll notice sine of pi by 2 minus x does not equal sine of pi by 2 minus sine x. Sine, you'll have to keep in mind, does not exist unto itself, okay? It needs an angle. So I cannot just take sin and start distributing it, right? Sine only exists when it has an angle. So we cannot expand. But let's check. So why does that? So not just taking my word for it, let's check. Why is this not true? So I'm going to pick a value for x. Okay, let's use something that we know. So let's sub in x equals pi by 6, right? So our pi by 6 angle. So if I were to look at this, my left side, this would become sine pi by 2 minus pi by 6, which we know pi by 2 minus pi by 6 would just give us pi by 3. So I have sine of pi by 3. Thinking about my special triangles, across from my pi by 3 angle, it's going to be my middle side length. So sine of pi by 3 is going to give me root 3 over 2. If I look at the right side, I have sine of pi by 2 minus sine of pi by 6. We know sine of pi by 2. Pi by 2 is on our vertical axis. Our vertical axis means our opposite side is 1. So sine of pi by 2, since sine is opposite over hypotenuse, that's going to be a 1. Sine of pi by 6, across from my smallest angle is my smallest side length. So sine of pi by 6 is 1/2. 1 minus 1/2 is 1/2. So therefore, our left side does not equal our right side. So again, our sine does not exist on its own. It has to have an angle. So do not expand a trig ratio. Okay, so do not expand when we are working with this. Okay, we know that sine of pi by 2 minus x equals cos x. It does not equal sine pi by 2 minus sine x. And this is going to become really important. Remembering that we cannot expand is going to be really important for a lot of the questions that we will be working with over the next day and a half. So our last identity that we normally do a really big proof for is our compound angle identities. So compound angle, you'll notice in our angle here, we have the addition of 2 angles. Again, you'll notice that we have cos of our first. So how I think about this is cos of our first angle, cos of our second angle, minus sine of our first angle times sine of our second angle. So cos A plus B, so that compound angle, is equal to what you read there. Cos of our first, cos of our second, minus sine of our first, sine of our second. So again, we cannot just expand it. It does not equal cos A plus cos B. You'll notice right there from that theorem that that is not true. What we have here is true. So normally, if we were in class with each other, we would go through and discover this proof. We would go through, how do we get cos of A plus B, and why is that true? That's normally a 30 to 40 minute proof in and of itself, okay? We are not going to go through that this year, okay? So you'll just have to trust me that this is true, and we're going to get good at using it, okay? So this is a compound angle that you need to know. We're going to build a number of other compound angles using our understanding of this compound angle. I will be posting a supplementary video on our compound angle identity and how to discover and prove this. So if you are still interested in that, there will be one posted for you to see, okay? But for the purposes of our time in this quadmester, we are not going to go through that full proof together, but we are going to get good at using it. So again, I've just rewritten out that proof using cos of A plus B, knowing that it equals cos of our first angle times cos of our second minus sine of our first, sine of our second. We're going to use that to discover our next compound angle identity, which is cos of A minus B. So we are going to use this identity to discover what cos of A minus B is. So let's start by writing it in terms of things we know. We have an addition, so you'll notice cos of A plus B, that is cos of our first plus our second angle. So there's an addition sign there. So the identity that I'm asking you to discover has subtraction in between. So let's first start by let's break apart A minus B and write it in terms of addition. This way, we can use our identity that we already know. And if we go back to our grade 9 integer understanding, we know that adding a negative still means we are just subtracting. So we have not changed mathematically the value of this. So now let's go through and use that. So our first angle we see is A. Our second angle we see is a negative B. So I have cos of my first, cos of my second, minus sine of my first angle, sine of my second angle. But we don't want to leave our angles with these negative angles in them. So, using our knowledge from in this particular lesson, we know that cos of a negative angle is equal to cos B. Sine of a negative angle equals negative sine of that angle. So now, using that previous knowledge that we learned earlier in this lesson, where we see a cos of negative b, let's replace it with a cos b. Where we see sine of negative b, let's replace it with a negative sine b. So I'm going to have cos A, cos B, minus sine A times a negative sine B. So again, I've replaced just using my negative angle identities. And then let's just clean this up a little bit further. So I have cos of my first angle, cos of my second. A negative and a negative is a positive. So plus sine of my first angle, sine of my second. So now this is our second angle identity that we have for our compound angle identities. So let's look back at those again for a moment. So we have cos of A plus B is equal to cos of our first angle times cos of our second minus sine of our first angle, sine of our second. Cos of A minus B, so it's still a compound angle. It's just involving subtraction instead of addition, is cos of our first angle, cos of our second, plus sine of our first angle, sine of our second. So a couple of things that I want you to recognize when we're building these. For cos, our compound angle identities for cos, you'll notice when there's addition between our compound angle, we see subtraction over here. When there's subtraction, we have addition. Otherwise, you'll notice it's the same pattern. Cos of our first, cos of our second, sine of our first, sine of our second. So what's happening here is the same, right? Cos, cos, sine, sine. But what is opposite is when I see an addition sign, I know that the sign in between is opposite of that. So just something to maybe help you keep that in mind. And again, when we learn our sine compound angle identities, I will give you a few more tips to help you remember those identities. So we know, looking at cos pi by 2 minus x is equal to sine x. We proved that already using our complementary angle identities, and we provided a geometric proof for that. We can also use our knowledge of cos A minus B to help us prove this. So again, let's go through using our knowledge. We know that our left side here would be cos of pi by 2 minus x. And again, we cannot expand our trig ratio, right? So we have to use our compound angle identity. Okay, so I have cos of my first angle, cos of my second angle. The sine is opposite in between. And then I have sine of my first angle, sine of my second angle. So it's important to be able to recognize, once we've taken that first step, what angles can we actually calculate? Okay, and I'm hoping, looking at this, we can see I can calculate cos of pi by 2. I can calculate sine of pi by 2. However, I am unable to calculate sine x because I do not know the value of x, and I cannot calculate cos x. So we want to make sure that we calculate the values that we are able to. So this is a cos pi by 2, right? So cos of pi by 2, we know that pi by 2 is on our positive y-axis. It means our opposite side has a value of 1. Our adjacent side does not exist. It has a value of 0 because we have not moved left or right off of that axis. And we know that our hypotenuse is 1. So here, cos of pi by 2, cos is adjacent over hypotenuse, so cos of pi by 2 is 0. We said we cannot calculate cos x. Sine of pi by 2, sine is opposite over hypotenuse, so sine is a 1. And if we simplify that a bit further, we get that cos of pi by 2 minus x is equal to sine x. So that is the beginning introduction to using our compound angle identities. We are going to continue to build on that over our next 2 lessons.